In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 20. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with air breathing type transformer. In the present context, the majority of transformers rated above 10 MVA are equipped with an exterior expansion tank or conservator mounted above the main tank. During contraction and expansion of oil level causes what is referred to as transformer breathing cycle, as air is brought into the tank and then expelled again for the latter. At the time of contraction of oil level, the air from the atmosphere is drawn into the transformer, what is referred to as the breathing in of the transformer. It is therefore much crucial to prevent atmospheric moisture from entering the transformer, which can contaminate the insulating oil and cause multiple damages over time to internal parts. To provide silica gel breathers fitted to the conservator of oil-filled transformers are the most economic and efficient means to absorb the moisture in the air sucked in by the transformer during breathing process. An oil seal cup is also fitted with the silica gel breathers and acts as barrier between silica gel crystal and air. Dust particles in the air would have to get trapped by the oil in the oil seal cap. Silica gel breathers are fitted with blue silica gel when installed and turned to pink color, which indicates that the silica gel has become fully saturated, that is, no longer absorb atmospheric moisture, and the crystals should immediately be replaced. Now see the diagram of the breathers. This is the connecting flanges, top lid, transparent cylinder, silica gel, bottom lid, air inlet, oil, and oil cap. Now, purpose of creating a nitrogen blanket. For maintaining the superiority of insulating oil properties, some of the power transformers are preferred to provide positive pressure nitrogen gas pressurizing the system for blanketing the transformer oil in the conservator tank from exposure to both oxidation and moisture. Nitrogen is generally be the best choice as the blanketing gas because of its inert properties, availability, and relatively low cost. Nitrogen is fed at the empty space of the conservator above its requisite oil level through a pressure regulating valve. Nitrogen regulating unit is comprised of a nitrogen gas supply cylinders with its own control valve, a simply supply pressure gauge, a three-stage pressure reducing assembly, and requisite piping and valves for regulating flow of nitrogen gas to and from conservator. Transformer breathes out while oil level starts to rise and the nitrogen inside has to release into the atmosphere. At the time of contraction of the oil level, fresh nitrogen is fed into the conservator tank from the nitrogen gas supply cylinder. Now, let's discuss with hermetically sealed transformer. Transformer of hermetically sealed type is the most widely used in the world. To restrict the substantial aging of cellulose and oil insulations, hermetically sealed transformers over conventional transformers have become the optimal solution. Hermetically sealed transformer is basically designed to construct with a view to keep the dielectric insulating fluid in the completely sealed transformer tank. With having the provision of conservator and breather, such transformer is simply equipped with the hermetically sealed enclosed tank and fins that would have to permit the cycle of temperature related volume fluctuations of the dielectric insulating fluid of the transformer. Fins, once welded, has become an integral part of the main tank structure. Hence, the total tank surface active area is therefore to be increased, resulting better provision of heat dissipation process. See the diagram, that is hermetically sealed power transformer of 80 MVA, 110 kV voltage rating. Sealed tank as equipped with fins that has to allow the oil expansion at the temperature variations. So tightness of the tank should have to be made up to a limit of 0.5 bar. In the hermetically sealed transformer, as the dielectric insulating fluid does not come into contact with the air, so its electrical properties are never be aggravated by oxygen and moisture, ensuring a long lifespan of the transformer. Such type of transformers must have a longer service life along with a high degree of operational reliability, as the complete insulation system is not at all subjected to load or temperature depending aging. In transformer industry, the impact of low losses and low noise level as compared to traditional conservator type transformers would have the primary reason for the worldwide extensive use of hermetically sealed transformers. Low maintenance is the added advantage which has to ensure low life cycle costs and reduce downtime. At present context, this technology is available with ratings up to 8000 kVA. Hermetically sealed type with nitrogen gas padding oil filled transformer. Most of the hermetically sealed transformer tank is not equipped with pressure relief valve. Also, there is no provision of implementing Buchholz relay in hermetically sealed type transformers, as because Buchholz relay is only to use with conservator type transformer. Whenever transformer has undergone any sort of abnormal thermal and electrical stresses, certain gases are produced due to decomposition of transformer oil. If such type of overheating has been constant phenomena due to ongoing arcing inside the tank, then production of decomposed gases would have become much more significant. As there is no provision of pressure relief device, so gases trapped inside the tank are not able to escape, which can cause damage to the structure of the tank. To encounter such type of problem, a padding of positive pressure nitrogen gas is kept over the dielectric insulating fluid in the transformer oil tank. Now, reason for using nitrogen gas as a sealant medium. Number one, having a strong dielectric potency around 2 to 3 times the air potency. Number two, colorless, odorless, non-flammable, non-toxic, more or less inert in gaseous form. Number three, nitrogen gas does not react with moisture. Number four, thermal conductivity is 2 to 3 times more than that of air. Number five, better heat transfer capability. Number six, superior in cooling properties than that of air. Number seven, gaseous nitrogen is valued for less expensive than the other inert gases, and thus the very little reactivity under normal pressure and temperature. Number eight, in the gaseous form, nitrogen is commonly used to seal potentially reactive materials from contact with oxygen for safety or for quality control reasons. In hermetically sealed transformer, which is entirely filled with oil and having no gas blanketing, has some limitations in size and capacity. It is as because the total heat dissipation has only been catered by the all four walls of the tank, which are subjected to corrugation to form fins. So it is always be better to keep the oil temperature sufficiently low. Hermetically sealed transformer of having nitrogen gas blanketing system, there is also have some drawbacks during abrupt cooling and in contraction phase of the dielectric fluid inside the tank. Though the solubility of nitrogen in transformer oil is relatively low, but solubility of nitrogen is exhibited while the temperature lies between 27 degrees centigrade to 88 degrees centigrade. Most important, though the solubility of nitrogen in transformer oil is relatively low, but solubility of nitrogen is exhibited while the temperature lies between 27 degrees centigrade to 88 degrees centigrade. It somehow, the oil would have been supersaturated with nitrogen, then due to formation of microbubble within the fluid may lead to have an instance of homogeneity in the dielectric oil insulation part. In construction phase, another basic constraints would have been faced during fixing of bushings. Further design orientation to counter all these limitations. Design orientation so far been achieved by implementing load-induced pressure changes, and that has been established with the application of introducing combination of following features. That is, one, exclusion of air, exclusion of extra gas space in the tank. Number three, exclusion of possibility of accumulation of decomposition products in the oil. Number four, transformer tank is made to connect to an enclosed space filled with nitrogen at very low pressure, approximately 0.2 kg per centimeter square to 20 degrees centigrade. A pressure gauge is therefore mounted on the main tank gas space area where filled with slightly pressurized dry nitrogen above the oil, and it is obvious that the positive reading shown in the gauge indicates that no water or air has leaked to the interior of the tank. Due to constant variation of oil temperature with load, the expansion and contraction of oil level would have been nicely entertained by the tank connected enclosed space filled with positive pressure dry nitrogen gas. To accommodate such type of implementation, the system is therefore to be further equipped with certain additional attachment, which includes 1. A nitrogen gas cylinder, 2. 3-stage automatic pressure reducing valve to maintain nitrogen gas flow to supply at the space above the oil as corresponds to transformer tank pressure. Whenever tank pressure exceeds its set value, then the regulator assembly has to actuate and vent out the excess nitrogen to atmosphere. High and low pressure gauges. High and low pressure alarm switches actuates when gas pressure reaches an abnormal value. Number 5, an oil condensate sump which equipped with drain valve so as to collect and remove condensate and oil from the gas. An automatic pressure relief valve to release the gas from the transformer so as to limit the pressure in the transformer to a safe maximum value. And number 7, necessary piping with requisite connections. Now, points to be noted. With the rise of temperature, transformer oil expands, resulting an increase of internal pressure, which may have to be relieved through the attached nitrogen gas system. Accordingly, during low load condition, when the temperature drops back, then internal pressure would have to drop and nitrogen gas may have to enter, depending on the extent of the temperature variation and pressure set point of the system. See the diagram, nitrogen system in the transformer. Pressure vacuum gauge, gas space, pressure range 0.03 to 0.5 kg per centimeter square, low pressure alarm, bypass valve, pressure gauges, sump, exhaust valve, relief valve, 3-stage automatic pressure reducing valve, and nitrogen gas cylinder. Transformer cooling methods. While a loading process that has been entertained by an oil-filled transformer, then it has to undergo an electrical process as well as being experienced through a thermal process that is driven by heat. If this heat is not dissipated properly, the temperature of the transformer will rise continually, which may cause damage in paper insulation and liquid insulation medium of the respective transformer. So it's essential to control the temperature with the permissible limit, and that has to ensure the long life of the transformer by reducing thermal degradation of the insulation system. Permissible temperature rises are mostly dependent on the method of oil circulation through the windings as it is heated up and then passing through the radiators to cool down. Circulation mechanism for the cooling medium would therefore be designed with respect to specified rating of the transformer and respective thermal dissipation process as corresponds to its operating conditions, such as at base load and during peak load. Cooling methods for dry type transformer. Basically, two types of cooling methods are very much applicable in case of dry type transformers. One is air natural, another is air blast or forced air cooling. Air natural, in this method, the temperature of the transformer while would have to become higher as compared to the temperature of the surrounding air. Then by the process of natural convection, heated air is thus to be replaced by cool air. This method is also to be denoted as a self-cooled method. Dry type transformer up to a capacity of 3 MVA is allowed to have a type of totally self-cooled by the circulation of natural airflow surrounding it. However, operate under normal conditions with forced air cooling, the output capacity of the transformer would have been enhanced by 40% to 50% in case of any intermittent overload or emergency overload operation. Number two, air blast or forced air cooling. Dry type transformer rated more than 3 MVA is always recommended for using air blast or forced air cooling arrangement. Dry type transformer with cooling accessories should have to be kept within stainless steel enclosure. According to size and capacity of the transformer, effective airflow system for total heat dissipation can be made to design by implementing requisite impeller diameter of the cooling fan, airflow entry point, position and angle of the air duct for top and side blows to high HV or LV winding, and also that of iron core. Airflow entry and exit ducts are suitably equipped with protective mesh door so as to ensure safe and reliable operation. A continuous blast of filtered cool air arrangement can have to be deployed for dry type transformers up to a rating of 15 MVA. See the diagram, dry type transformer enclosures. Dry type transformer with cooling accessories. Cooling arrangement for oil-immersed power transformers. In conventional oil-immersed power transformer, the temperature at the top of the windings is always be higher than that at the bottom because oil flows from bottom to top with a continuous temperature rise, which has to weaken the cooling capacity of the oil. It is obvious that the cooling of the transformer windings would have the most important thermal aspect of the transformer design. But considerations would never been denied regarding the significance of heat as generated by the core, leads, and internal structure steelwork during operating sequence of the transformer. Out of these, the core is the most significant one and also vulnerable as because there is no specified maximum limit for the temperature rise of the core in any of the international standards. The core heat value and its dissipation must have to depend on grade of iron and its flux density. However, the direct heat transfer from the core surface to the surrounding oil is usually followed the criteria of natural oil circulation. So, typically identified, all the internal temperatures are therefore transferred to surrounding oil, resulting a sharp rise of temperature of the corresponding oil. To ensure about the cooling of the warmed up oil, there would have been a design provision which must be accomplished with means of dissipating heat energy to the surrounding ambient or atmosphere. In order to maintain sufficient operating temperature and for avoiding unwarranted temperature rise of the oil, various cooling arrangements are taken up. One, oil natural, air natural, that is ONAN type. Number two, oil natural, air forced. Oil natural, air forced, that is ONAF. Number three, oil forced, air forced, OFAF. Number four, oil forced, water forced, OFWF. Number five, oil directed, air forced, ODAF, or oil directed, water forced, ODWF. Designing an effective transformer cooling system may have to enhance the transformer capacity by 30 to 50% of its capacity. Now let's discuss with ONAN, oil natural, air natural cooling system. The full form is oil natural, air natural, and it is one of the simplest method of oil filled transformer closed loop cooling system. In this method, hot oil circulation is being subjected to keep following continuously by the process of natural thermosiphon mechanism, as due to the major cause of gravitational buoyancy convection of the oil in the closed loop cooling system. Core and windings are the principal sources of losses, causing rise of temperature in various parts of a transformer. As the winding and core are totally submerged in the oil, so the heat transfer mechanism through natural circulation of oil has there to be taken place by three modes. One, conduction, convection, and radiation. Heat as generated by the core can flow directly to oil. Heat as generated by the copper metal of the winding has to flow through several layers of insulation provided on the winding conductor to reach the cooling medium, that is oil, due to the conduction of heat transfer mechanism. Therefore, as the oil being a liquid has taken all the heat so far been generated, its density or the specific gravity would have to reduce with the increase of oil temperature. This has resulted a change of volume with temperature, and hot oil starts flowing from bottom to top via convection. Thus, a continuous oil circulation process is being established within the tank and radiators, which provides an essential effect of convective or thermosiphon cooling system of the oil. Heat from core winding and structural components is dissipated by means of the oil circulation and is finally transmitted to atmospheric air from transformer tank equipped with radiators by means of both radiation and natural convection. For higher rating transformers, the tank surface area are usually designed to provide much larger heat dissipating surface in the form of radiator tubes or radiator banks mounted directly on the tank or mounted on a separate structure. The cooling of radiators would also occur by radiation, but because of closeness of radiator fins, the entire radiation surface does not participate in the heat transfer mechanism by radiation. Thus, the effective area of radiation can be taken as the outside envelope surface of the radiator. Now see the important points. Thermal radiation would always be referred to energy emitted by objects due to their temperatures. Hence, radiation does not require any medium between cold and hot surfaces. The emissivity of the radiating surface would have to affect the radiation and must have to depend on factors like surface finish, type of paint applied on the surface, etc. If the emissivity factor, if the emissivity factor is found to be less than unity, then it indicates that the effective radiating surface is correspondingly less. Most of the cases, transformer tank and radiator banks are thus to be painted with gray color, which may have to achieve the effective radiating area of emissivity factor of 0.95. It has been exhibited that radiation heat transfer mechanism on cooling performance of radiator banks in transformers equipped with air natural cooling, that is ONAN type cooling configuration, has to contribute approximately 20 to 22% of total heat dissipation, and the rest portion would have been by means of convective heat transfer mechanism. Occurrence of heat dissipation by means of convective heat transfer mechanism is much more evident, as because it has been observed that the convective heat flux is of much higher than the radiative heat flux for the radiator bank middle fins, whereas the effect of radiation is much more pronounced for the radiator bank end fins. Radiative heat flux distribution over the radiator bank end fins is quite significant, as these fins are directly exposed to ambient air and can have to radiate freely to the environment. Cooling capacity of an ONAN type power transformer radiator can be well established while designing with proper computation of optimum space between sections having with optimum length of sections of radiator. Power transformers with higher capacity are usually equipped with detachable radiators, which would have to act as steel plate heat exchangers that are installed vertically next to transformers, that is in the figure 93. Optimization of thermal head of radiator banks is one of the most crucial factors for increasing the rate of oil flow, and the heat dissipation process. The thermal head is thereby determined by the difference between the center of gravity of the oil in the tank of and of radiator bank. The higher thermal head of radiator banks that would have been achieved by adjusting the height of the support structures of the radiator banks. When radiator banks are being mounted at higher height, then there would have been an increase of the buoyancy effect on the cooling loop, resulting an increase of the rate of oil flow and thus causing a better heat dissipation criteria. However, an increase in oil flow rate may have to instigate an increase of frictional pressure loss within the radiator banks, causing some extra amount of heat. So, the thermal head gained by the height difference would thereby have been countered by the effect of heat as produced due to of such type of frictional pressure loss. Under ONAN cooling system, the oil flow rate inside the windings is normally guided by the natural balance between the viscosity level of the oil and the thermosiphon pressure head. Viscosity is one of the most important properties of transformer oil, as because it is directly associated with the heat exchange process. Oil viscosity is thus to be determined by measuring the amount of resistance as offered by the oil during its continued flow, even in normal operating temperature. Viscosity of the oil decreases with the rise of temperature and vice versa. Since operating conditions of power transformers are always be characterized by elevated temperatures, so selection of oil viscosity index has to be made when oil is heated. For an effective heat transferring process, transformer oil must have to retain a low viscosity index all through at its operating cycle. However, oil viscosity index would have to vary gradually with the decrease of oil temperature. ONAN type cooling system is generally applicable for oil-immersed transformers up to a capacity of about 30 MVA. Now see the detachable radiators of power transformers. Oil is kept in circulation by the gravitational buoyancy in closed loop cooling system. This is the ONAN type cooling transformer. Oil flows from tank to radiator and back to tank due to thermosiphon effect. Air natural cooling configuration for oil field transformer, where heat is produced from core, windings and structural components is dissipated by means of the oil circulation and is finally transmitted to atmospheric air. 1. From core, heat flows directly into the cooling medium, that is oil. From winding, transformer of heat to oil is followed by conduction heat transfer mechanism. Number 3, heated oil flows in the upward direction and then transfers its heat to tank and radiators by means of convective heat transfer mechanism. Heat would have to transfer from inner surface to outer surface of the steel tank and radiators by means of conduction heat transfer mechanism. Finally, heat flows through convection and radiation from the radiator fins to the ambient air. These 5 points are to be noted. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.